Okay, so I've saved this page as a standalone mini lecture because carbocation rearrangements can get a little tricky, and so we need to spend a good amount of time just focusing on those alone. And so we have done examples of the 1,2-methyl shift and the 1,2-hydride shift, but I also want to cover those again with a different molecule and show ring examples where they can undergo to expansion or contraction, and how resonance can also play a role in making it look like the rearrangement has happened where the nucleophile ends up on a different carbon than where the leaving group was. So I'm going to go through those 5 steps or those 5 possibilities using 5 different examples, and they will each correlate with one of those. So this would be, I'm going to demonstrate a methyl shift there. I'm going to demonstrate a hydride shift there, a ring expansion here, a ring contraction in this one, and an example of resonance in this scenario. So let's start from the top and look at the directions. Each of the following structures undergoes savolysis. Remember what that means? The solvent is your nucleophile. When treated, so let's write that here, solvent equals nucleophile, because they're breaking up the solvent. When treated with ethanol, there's our nucleophile right there. Draw the first order. The only first order thing we've learned about so far is SN1. Major products of the reactions below. Hint, these will all undergo the rearrangements listed above. So number 1, we have a carbon with the leaving group attached. That's our substrate. That's for the electrophile. Our nucleophile is going to be the ethanol. You always want to identify those before you move on. You find the leaving group. That's the carbon that's going to become our carbocation. Since we're doing first order, we have to have a carbocation intermediate. So let's go ahead and do the first step, which is now that we found the leaving group, let it leave and draw the consequence of it leaving. So we have a carbocation there. Now what is the substitution pattern of that carbocation? Secondary, right? Because we have a carbon with 1, 2 groups attached that are carbons. The other one that was attached was a hydrogen. So it's a secondary carbocation. If we could make it tertiary or provide resonance, those are the 2 things we can always do to make it more stable. So let's see, what can we do? We look at the carbons adjacent to the carbon, that's the carbocation. So this one has 2 H's and a C. This one has lots of methyls. So that kind of screams out to you, we can do a 1,2-methyl shift. If we take one of those methyls and bring it over here, then we have a carbocation here now instead of there, and that would give it a bigger substitution pattern, namely tertiary. So let's go ahead and do a 1,2-methyl shift. So if we call this carbon 1, that's carbon 2. We take a methyl off of carbon 2, give it to carbon 1, and that's our 1,2-methyl shift. Now notice as a consequence, now the carbocation is here because that's the carbon that lost some electrons. Notice it has 3 bonds to carbons, therefore it's tertiary. I did it in green since I did that in green last time. And so since it's tertiary, we have successfully stabilized our carbocation. We did a 1,2-methyl shift. I usually like to write that out in words as well. So 1,2-methyl shift. All right, so now it's ready to form the product. So remember that ethanol is our nucleophile. We're doing savolysis. So here comes ethanol, which we can abbreviate ETOH. And it's going to use the lone pair to attack the carbon that has the carbocation. Then we draw in the new bond to oxygen. Oxygen is the one that attacked. Oxygen still has all its attachments. It has the ethyl group and it has the H, and it's positively charged now. So because it made a 3rd bond, that oxygen is positively charged. Now I'm just realizing I dropped a carbon along the way. Let's fix that. So starting from here, we had an ethyl attached to the carbon that had the leaving group, so that's correct. But then this needs that carbon there. So one more. There we go, that's better. All right, so we're not quite done. We're almost there though. Because now we're used to acids and bases. This is easy stuff now, right? So we can do this deprotonation using the lone pair, leave the electrons behind on oxygen, and we will write out our final product. OET, We made an ether in place of where the halogen used to be. Now, do we describe this as racemic? No, because this is not a stereocenter here. Is there a stereocenter here? Yes, there is. So this one has 2 methyls. That's not a stereocenter. Now this one was planar at this point, and then we did the methyl shift. So we could have had the methyl sticking out or going back. So I'm just going to write plus or minus. This is a stereocenter. I'll write plus or minus right there, just to be thorough. Okay, that was a 1,2 methyl shift scenario, so we're done with that one. Now we're going to do an example of a 1,2 hydride shift. Notice the substrate's almost identical, except it's not a T-butyl group, it's an isopropyl group. What's different about that is that if we were to do a methyl shift, we would not get a tertiary carbocation here anymore. So it's not favorable to do that. So let's start drawing that out and see what happens. Since we know we're doing SN1, this first step's always the same, leaving group leaves. And you can go from there. So we have our new, let's go a little too messy and fast, there we go. New carbocation. And yes, it is secondary, just like before. Now, if we were to do a methyl shift, just like before, and we took that methyl off and moved it over here, we'd have a secondary carbocation again. Not worth it, because we are starting with secondary. We don't want to end with secondary. This is when examining the possibility of a hydride shift is worthwhile. I'm going to draw in the H that's here. There's an H there instead of the methyl. If we move that to a 1,2 hydride shift, then we would end up with 2 H's here. Remember, there was one from before, and now I'll circle the one we moved. This is the one we moved, right? And just for clarity, I'll draw in one of the other H's. So now we have a carbocation here, which is in fact tertiary. That was a favorable move. That's when you want to do a 1,2 hydride shift, is when a 1,2 methyl shift would not do that for you. Now we're ready, we've completed our rearrangement, we're ready to let the nucleophile attack since we know we're doing an SN1. I'm going to draw ethanol this time just to switch things up a little. Instead of writing the ET abbreviation, I will write the ethyl out and attack the carbocation. The arrow lands on there. We have the H attached. Everything that was attached to the oxygen is still there. Now the oxygen has a positive charge, and we still have the bonds to what's now a propyl group. 1, 2, 3 carbons. And we're almost home. We just have to neutralize. That same step that we had at the end applies. So here it comes to neutralize. And there we go, OET. 2 methyls on a carbon, and then a propyl. Notice this is not a racemic mixture because there are no stereocenters. So we would be wrong to indicate that it's racemic. Okay, number 3, we are going to examine some ring scenarios. So notice that we're starting with a 4-membered ring. Doesn't matter, we're going to have the same first step though. Since we're doing SN1, it's first order. Leaving group always leaves first. Now, I mentioned we're starting with a 4-membered ring. And we know that 4-membered rings are less stable than 5-membered rings, which are less stable than 6-membered rings, right? So we want to consider the idea of using a shift to allow us to expand our ring size. So notice that we have our carbocation here. And yeah, it's secondary. But what would be nice is if we examined all of our neighboring groups that are attached. So H's are here, and then we have an H here. So we could do a hydride shift and make it tertiary. Doing a hydride shift here would make this one primary, so that's no good. So that would be worth considering. However, if we, instead of doing a hydride shift, if we did an alkyl shift, which is similar to doing a methyl shift. So in other words, if we grabbed one of these little pegs of the ring and moved it over, just like we would if it was a methyl, that means we have added a new carbon to the ring. We go from a 4-membered ring, so I'm going to write that out. I'll do it in green just so it's different. 4-membered ring. If we do an expansion, expand, I think I added an extra, let's see, if we do an expansion, we will get a 5-membered ring. Now sometimes that's hard to see, and notice that once this is the new bond here, this group is sticking out, so we still have a methyl sticking out of the ring. Let's number our carbons to make sure we didn't screw this up, because this is easy to go wrong. So I'll just start here arbitrarily, doesn't matter. 1, 2, 3, 4, 5, 6. So that means I have 1, 2, 3, 4, 5, 6. Now let's see if we can make sense of this. 6 broke its bond to 3. Now it's connected to 2. So 6 is not connected to 3, it is now connected to 2. 1 is external to the ring, 1's external to the ring. So now where is the carbocation? We still have it. We did not get rid of the carbocation. So it used to be on 2, but 2 gained electrons from 6. 6 actually is sharing them with 2 now. So 6 doesn't host the carbocation. Who lost electrons? We see that 6 and 3 broke their bond. 6 took the electrons away from 3 to share with 2. That means 3 now is missing electrons. That's the carbocation. Okay, so now that we know where the carbocation is, let's see if we made a good move. Well, we went from secondary to secondary. However, that's better because we now have a 5-membered ring. That's much lower energy. So that's favored over going to tertiary and keeping a 4-membered ring. We'd want to create ultimately the more stable product, because we're stuck with a 5-membered ring at the end instead of a 4-membered ring at the end, and that's a better thing. So we're ready to complete our savolysis by taking our ethanol and using it as a nucleophile to attack our new carbocation. And we have a methyl here, right? And then we have our O with all the good stuff attached that made it ethanol. And we got to neutralize that. Now remember, the O could have attacked from the front or the back here, right? So I'm actually going to make this a wiggly bond, just so we remember to define the stereochemistry later. It's a stereocenter. This is a stereocenter too, by the way, which could have formed from either direction. So we'll have a mixture there of possibility. So let's close this here. OET and methyl. And since we have 2 stereocenters with 2 possibilities, we have 4 possible stereoisomers. That means we have diastereomers. It's not a simple racemic mixture once you start to get 2 stereocenters that could have changed, especially with a rearrangement. Okay, so a lot in there. So once again, we did a ring expansion once we noticed that we could move our 4-membered ring and transform it to a 5-membered ring. All right, so we're going to do another scenario. This time we're going to start with a big ring that could actually contract. I'm going to throw on another carbon just to make this problem a little more straightforward. So I'll put one on there. So we have a 7-membered ring here. So we're going to ultimately think about contracting. You see a 7-membered ring or 8-membered ring, think about contraction. You see a 4 or 5-membered ring, think about expansion. We want to approach that sweet spot, which is a ring size of 6. All right, so regardless, our first step's always the same. Leaving group leaves. Then move on from the leaving group leaving. And notice you have to draw a 7-membered ring now, which no one really likes to do. But what I found easy is to start to draw a stop sign, which is an octagon, right? And then when you get to the end, instead of drawing the last side, just continue, make it a point. Yeah, that's a little longer, bonds in proportion, but at least it's not totally hard to tell what it is. Okay, so we have our carbocation because the leaving group left. So what we're going to do is a contraction. So the ring contraction will allow us to make sure that we get from a 7-membered ring to a 6-membered ring. And so we're not doing this necessarily to become secondary versus tertiary. We actually want a more stable product at the end, so a 6-membered ring over a 7-membered ring. So how could we do a ring contraction? Well, we can only do a 1-2 shift. So we could take a carbon from here and contract it, but then we'd have a primary carbocation there. But if we take the carbon from this neighbor and bring it in, then this ethyl would hang out of the ring, and we'd have as we take this off, we'd have a secondary carbocation. So that's by far more favored. I'm going to number my carbons so that this isn't too hard to follow, hopefully. So let's call it 1, 2, 3, 4, 5, 6, 7. All right, so in other words, when you do a 1-2 shift, if this is carbon 1, the one with the carbocation, the only carbons that are allowed to give any carbons to carbon 1 are carbons 2 and 7. So 7 would have had to break its bond with 6 to give it over, but that would get a primary carbocation. 2 needs to break its bond with either this methyl or the 3 to fill that carbocation. If it gives it a methyl, that does nothing. We still have a 7-membered ring. But if we give it the bond between 2 and 3, we break that and reattach here, we decrease the ring size. So let's try that. So I'm going to lasso the bond between 2 and 3, move it over 1. That's a 1-2 shift. So that gives us a ring contraction. Now that means we're going to have a 6-membered ring instead of 7. Let's keep numbering because that's going to clear it all up. So 1 is now bonded to, look back to see what happened here. 1 is now bonded directly to 3 in the ring. It's still bonded to 2, but 2 is outside the ring. 2 is part of what's now an ethyl group. So I'm going to write in the methyl just for clarity. So remember that 2 had that methyl attached? Oh, here's a methyl. Okay, 3 is still bonded to 4, still bonded to 5, 5 is bonded to 6, 6 is bonded to 7. So now we have our 6-membered ring. Notice that our carbocation is now here because 2 is the one that lost the electrons. Okay, so now that we've expanded our ring, contracted the ring, we can go ahead and take care of filling the open octet. Tack. All right, so that could have come from both sides. So this is now a new stereo center. And we can go here. Get to our final product. Hopefully we see now that we should have an O, T, and a methyl. How did we get there? We draw our ethanol as our base. And there we go. This is the depth of the complexity I usually expect students to know, but I'm going to write out just a nice little challenge example here. So this is a product we'd observe, and most of your homework will follow that sort of thing. But you can often do more than one rearrangement at a time. So notice that this is secondary, and we proceeded with that reaction without considering a second rearrangement. So just as a little bonus sort of challenge exercise, ask yourself, is there another route possible to come up with more products with different rearrangements? In other words, a second rearrangement. So kind of think about that after you feel like you're comfortable with this page and give it a try. The last example I want to show you is what happens when we have resonance with a carbocation. It can make it a surprise answer. So in other words, when we're thinking about SN1, we're going to say, okay, well, this is our leaving group. It's going to be gone. And then ethanol would attach here, but we'd lose the H. So then we'd have OET as the ether. So then that would make us think, well, okay, so if I'm going to predict this product without drawing a mechanism, I'm going to expect to have this, right? That's not going to be the correct product, which is why we always need to draw the mechanism, always. So what actually forms, so I'll erase this one, is the ether ends up way up here. This is a racemic mixture. So how does that happen? Well, the mechanism will explain it. So let's show how that worked. Leaving group leaves, always the same first step. Secondary carbocation. Notice that it's allylic. I'll write that down. Whenever it's allylic, it's always worth drawing the resonance structures adjacent to a pi bond to see what possibilities are there. So let's draw the resonance, and that means we have this scenario. So where's the carbocation now? Well, once we move the pi bond here, this is now missing it, so that's the carbocation. Okay, now that is a tertiary allylic position. Since that is better, we are going to proceed with the tertiary because it's more stable. So that means when ethanol comes along, it's going to attack that tertiary carbocation instead. And then we have our scenario where we have since that was planar, it is now creating a stereocenter when you attack from either side. We still have our H attached. And then to finally get home, we do our neutralization that we've been doing. So as you can see, we didn't actually move carbons around, but we moved reactive sites. So in a simpler SN2 reaction, the new group always goes on the carbon where the leaving group was. But in SN1, because rearrangements are possible, it's not always so simple.